unit on, or I should say our first section on the blood and blood spatter unit. Just to get this out of the way, if you hadn't caught this earlier, spatter is actually what it's referred to. I get that that looks kind of like it would be blood splatter, but it is a spatter. So this particular section, or this first chunk that I go through with you, it doesn't really deal so much with the forensics as it does just, look, here's an intro to blood. These are the components of blood. And then we wrap it up with looking at blood typing and compatibility. So, we'll kind of finish up with that portion. I will say, though, that the blood typing is pretty valuable in forensics because it's a very quick way of, if your suspect has type A negative blood and the type that you found that didn't belong to the victim was B positive, you can kind of assume it wasn't their blood. But we'll get into all that a little bit later. So the objectives here, what I'd like to get through again is just the basic components of blood and their basic roles. I stress basic because we're just kind of scratching the surface here. If you've got interest in it, I would encourage you to take anatomy physiology, where you can go into these topics in greater detail. We'll look at what the ABO system is and why type A blood is type A, or if we say it's positive or negative, what the heck does that mean? And then we'll start to look at the recipient donor for different blood types. So to get rolling here, what the heck is blood? Blood, it is going to be a tissue, and there's basically three parts to it. There's three solid parts, I should say, which makes it a mixture. And they're going to be suspended in what's referred to as plasma. So if you're looking at the picture here on the left, you've got your two test tubes, right? This one is probably what you think of as blood. It's whole blood. It's got a reddish color. And if we look at this whole blood and say we were to take this vial and put it in a device called a centrifuge, what a centrifuge basically does is it spins things around at a very high speed, and then they'll separate out by density. And depending on where you're with chemistry and physics, you should know that more dense objects sink and less dense objects. So if we look at the vial over here on the right, that's going to be whole blood that's separated out into its components by density. You've got red blood cells, you've got your white blood cells and platelets here in the middle, and then this top portion would be the plasma. The plasma is what these other parts are suspended in. And by other parts, I mean your red blood cells, your white blood cells, and your platelets. Notice over here, RBC, that's the abbreviation for red blood cells. You may find that easier to jot down in your notes. And here we've got WBCs, which stands for white blood cells. Platelets, I don't know, sorry, you got to write out platelets. But these are the three solids that are again held in suspension in this liquid portion of blood called the plasma. So we'll start with red blood cells, or as they're technically known, erythrocytes. So your erythrocytes, or your red blood cells, they're going to be basically responsible for carrying gases. Oops, I should have O2 there. I just have O for oxygen. And CO2, that's your carbon dioxide. Basically, you take a deep breath. Exhale that out. You brought oxygen in, and you've carried CO2 out. That's going to be basically what your red blood cells, or your erythrocytes, are responsible for. Red blood cells, as the name suggests, they have a reddish color, and that's going to be from the hemoglobin. That's going to give the blood the reddish color, and there's actually some iron in there, and we'll discuss that in just a moment. Oops, sorry, let me backtrack here. Take a picture, take a peek at the picture of this red blood cell, or this RBC, or this erythrocyte. So they kind of have this like little squished center. That actually adds for more surface area. So, you got to figure if these guys are responsible for carrying oxygen in and carrying CO2 out, you want them to be loaded up with as much as possible, right? So this little squished area here gives it a bit more surface area, and that allows it to do its job better. Maybe you've heard of sickle cell anemia. Sickle, it's like, at the Grim Reaper would carry, or something that in the olden days would be used to hand cut down like wheat or something. It's got basically like a crescent moon or kind of a banana shape where it's sort of pointy, and with that it can't carry as much of the gases, your oxygen and your CO2, and those pointy shapes can actually cause a lot of discomfort. So we don't need to go too far into that, but just to quickly recap here, your red blood cells, your RBCs, they're referred to as erythrocytes, so that's their technical term. Their primary role is to carry gases, oxygen in and CO2 out. And the fun fact here is hemoglobin is what's responsible for giving blood its reddish color. Guess what this guy is? A booyah. That's your white blood cell, or your WBC, or their technical term is leukocytes. And what we need to know about white blood cells is that it's responsible for, basically it's kind of like your line of defense. It's going to fight off disease, or if something is perceived as an invader, your white blood cells come in and they're going to basically kind of try to fight off or attack or contain that disease. So, excuse me, in the world of forensics, we like what blood cells, or we're concerned with the leukocytes, because this actually contains DNA, which we'll see is a pretty major role for forensics. Looking at our white blood cells, or our WBCs, again, we should know that their technical term is a leukocyte, that it's going to be a primary role of like fighting off disease, or help keeping you from getting sick. And our fun fact for our leukocytes is that it contains DNA. Look at these little rascals. Got those little squiggly arms. Fun to look at, fun to say. Platelets, or in my opinion, the funnest word of all the, or more fun. I guess funnest isn't the word, right? The thrombocytes. Let me just get moving here. Thrombocytes. I like that word. That's the technical term for platelets. And if you take a pic here of a platelet, what I think stands out, or what is notable, is it's got these little grabbers, right, or these little arms. And that's so that your platelets or your thrombocytes can kind of interlink. And platelets aid in clotting. So if you cut yourself, you could bleed. Why do you stop bleeding? Because platelets come in and help us out. They're going to aid in clotting, and they're going to repair damage that might be done to those blood vessels. And these little squiggly arms on the thrombocyte, they're going to interlink, and that's going to help you stop bleeding. If you've ever had a scab that's formed from a cut, essentially what you're looking at is a bunch of dried platelets or thrombocytes that have made their way to the surface there to help repair and aid in that clotting, so you don't bleed out. Plasma. Looks like a sack of pineapple juice or something there, right? That is actually just the plasma, or the liquid portion of your blood. And in suspension, you've got your red blood cells, your white blood cells, and your platelets. So what we're looking at here is just plasma. Remember that device that I was telling you about, a centrifuge? If you put whole blood in there and separated out all those components and just took out the liquid portion, or the plasma, that's what it would actually look like. It's got that kind of orangish color. Cash, blood's red. What gives? That's true. Your red blood cells, or the hemoglobin, is what gives it its reddish color. So if we go back to this, your blood, it is a mixture. You've got all these components that are sort of held in suspension and in the plasma. Your red blood cells and your white blood cells and your thrombocytes, or your platelets, right? And we know that if we were to put those in a centrifuge and have it all separate out, we would have these different components. Here's a question for thought. I'm looking down here, and there's my red blood cells at the bottom. All right, we said those must be the most dense, but then I'm looking at this little strip right here between the red blood cells and the plasma, and there's not really very much, by comparison, white blood cells and platelets. Why do you suppose there would be so many more red blood cells than there are white blood cells and platelets put together? Well, let's go back. Think, what's their primary roles? Remember, red blood cells, their primary role is to bring in oxygen, get rid of CO2. Platelets, primary role is to help you with repairing damage or clotting so you don't bleed out. And white blood cells, they're kind of like your defense system, right? So what's more important? And I'm not to say that that means that, or it implies that the others are not important, but breathing, not bleeding, fighting off disease. Breathing, right? I mean, that's going to be something that has to be done on a regular basis, or a much more regular basis, I should say. So long story short, you have more red blood cells because they're basically helping us with that cellular respiration or the breathing that constantly must occur. So we're going to skip past these little videos. I'm going to link them by themselves just in the interest of time and keeping this video a little bit shorter. Every now and again, YouTube gets kind of funny about what's posted and what's not. So I'm going to try to link these individually. As we go through, if you see a slide or in your notes where I've asked you about the particular video, I'll just link those on their own. And you can just sort of skip past those for now as we continue forward. Here we see Carl Landsteiner. And the reason that we discuss Carl Landsteiner and his work, it turned out this guy won a Nobel Prize. I mean, he was a genius. There's an awful lot of contributions he's made to science, but we're talking about him here in this particular unit for forensics because of what Mr. Landsteiner did with blood typing. So what he noticed was that sometimes with transfusions, it could be life-saving. You give someone else's blood who, say they're undergoing a surgery, or maybe they bled out in the battlefield, or whatever the case might be. If you lose too much blood, it can be fatal. That's not good. And what they found is sometimes you can give people someone else's blood, and it works out to be a lifesaver. And other times, you can give someone else's blood, and it does not go well. The blood clumps up, and it could actually cause death. That's not what you want to have happen. So Landsteiner did some work and figured out why this occurs, why sometimes transfusions, sharing or giving blood to someone else, could be a lifesaver or a life ender. And what Landsteiner discovered was that there's different proteins on red blood cells. And these different proteins sometimes work well and sometimes not so much with each other. But before we get into that, this is what he described as the ABO naming system. And the ABO naming system basically just tells us, let me go back here, what proteins are or are not present on the surface of a red blood cell. So if you look at this picture here, this is going to just kind of visually show us. It doesn't mean that your A protein or your type A blood has little yellow circles on it. They've just tried to show you, okay, here's type A blood, and it's got the A protein on its surface. If I look at this guy here, it's again, not to say that the B protein making this type B blood is these little yellow triangles, but visually it just shows you, okay, these are different proteins on the surface. So type B blood would have this B protein, the second one that Landsteiner discovered on the surface of the red blood cells. If you look at type AB blood, sometimes a common misconception is, oh, okay, well, this must have an AB protein. No. You've got both the A and the B protein on the surface of that red blood cell. So if we look at this, right, we see the little circle guys, and we see our little cone guys. So these are both these proteins on this surface. And then if I jump over here, check this out. Type O blood, it's just a blank red blood cell. So again, another misconception that happens is, okay, yeah, I got it. So type O must have the O protein. No. Type O blood has no proteins on its surface. So if we look at this simple model here right now, you've got 4 blood types, but how many proteins are we dealing with? A lot of times kids will think, well, you got 4 blood types, you got 4 proteins. No. We're really only dealing with 2 proteins. And down the road, we'll see there's actually a lot of other proteins that can exist and they help us with probability. But right now, we're just kind of, scratching the surface on this. But check this out. There's 2 proteins that make up 4 blood types. If you've just got the A protein, you're type A blood. Just the B protein, type B. Both of those proteins, you're type AB blood. None of those proteins, it's type O. So the reason it's called the ABO naming system is it basically tells you what proteins are or aren't present on the surface of a red blood cell. Here's another visual way of looking at it, and this should kind of make sense. The fact that they switched up to triangles or circles here, that's irrelevant. It's just visually trying to show you, hey, look, here's an A protein, here's a B protein. So type A has got, in this case, triangles. Type B, in this case, has blue circles. AB, all right, I know that should have both those proteins. And they've showed us that with both triangle and circle. Type O, no proteins. Notice that it is just a blank red blood cell. We're going to skip past this, and I'll link the little Bill Nye video here for transfusions and some of the contributions Landsteiner made to it in a bit. But we're going to move a bit forward and take a look at this flow chart. I call this a flow chart just because it kind of shows you a bunch of information. But this is going to be the intro to compatibility. And I'll have this on your test, so you should be familiar with it. You've got to be able to kind of work through, all right, well, looking at this, does this remind me of what blood types could go to what types? Or who could receive or who could donate to who and why? And looking at this, I will say that it's simple in that it does not take into account positives and negative blood types. But I'll give you a second just to look this over, and then I'll explain. See if you can kind of try to figure what's what with it. Okay, so this tells me we've got type O blood up at the top, and it looks like type O can be given or could donate to type A, to type B, and to type AB. This looks like type A can donate to itself and and also type AB blood. Type A can't donate to O, type A can't donate to B. B could donate to itself, could donate to AB, can't donate to A or to O. And then you can kind of carry that logic out. So a question that might come up is like, whoa, why? Here's the thing that I really want you to get with all this. You can only donate to a blood type that's not going to get a protein that the body's not used to. Or maybe another way I could say that is, you can donate blood types, you could donate from one blood type to the next as long as you aren't receiving a protein that your body's not used to. So here, let me give you an example. If I have type A blood, which I do, but that's irrelevant. Say I got type A blood. Why can I receive type O blood? Well, what proteins are on type O? None. So if I get type O blood, am I receiving any proteins that my body's not used to? No. So I don't have a problem with that. A question that'll come up sometimes though is like, yeah, but Cash, you're type A blood. You're not getting that A protein. That's okay. You don't have to get all the proteins that your body's used to, or else then you just have to have like type A goes to type A, type B goes to type B, or whatever. So with that being said, let's look at it the other way. Why can't I donate to a type O person? Well, if this person's type O, they have no proteins on their red blood cells. I'm type A, I've got that A protein. If I give my blood to this person, they're going to receive that A protein. Their body's not going to like it. It's going to treat it as a foreign invader. In come the white blood cells. It's going to try to clump it up and contain it. And it could actually be fatal and kill that person. The reverse of that is this person can give their blood, by this person I mean type O, could give their blood to everybody because they're just a blank red blood cell. Anybody gets that blank red blood cell, there's no problems there. There's not going to be any issues. They can be basically what we refer to as the universal donor, which is to say they can donate to everybody. Look at this little piggy down here, type AB blood. Who can they receive from? Everybody. Why? Well, because they've got the A protein, they've got the B protein. So that means that they can get type A blood. Hey, I'm used to that A protein, no problems. They can get type B blood. They can get that B protein, no problems. They can get the O blood. Everyone can get that. That's the universal donor. No foreign invaders, no proteins they're not used to. Everything's great. So type AB blood, that's referred to as the universal recipient because they can take everybody's. Now, here's another question for thought. With all that being said, and looking at this little flow chart, how many blood types could type AB give to? Not receive, but give to. A lot of times this is a point where kids will say zero cash, type AB blood can't give to anybody. And they can walk through the logic behind that. Here's actually the truth. Type AB blood can donate to one blood type, its own, AB. So I see kids a lot of times forget that blood types could donate to their own. So like if I show you this chart and I say, how many blood types from this chart can type O donate to? A lot of kids will say, oh, well, 1, 2, 3. And I'd say, keep going. 4. Type O blood, according to this, could donate to itself, type A, type B, and type AB blood. So this may be something that you have to think about and sort of work through a bit, which we'll do together later. But that's my intro with this compatibility. So how common is this stuff? Well, I guess you could make an argument that it's good that type O is the most common. Because remember, type O, they can only receive their own, but they can give to everybody. So that's the universal donor. And when I got this here, about 43% of the population had type O blood. If I jump all the way down to the little piggies, type AB blood, or the universal recipient, only about 3% of the population has that. And then 42% and 12% respectively for types A and B. So this just gives you kind of a ballpark, again, when this was made of how common these were. I'm sure there's a little bit of fluctuation, though. Oh, look at those cute little critters. These little rascals here. These are rhesus monkeys. And along came Alex Weiner. And Alex Weiner in the 1940-ish era was working with rhesus monkeys. And this led to the discovery on their blood of another protein. And as they went back and they looked at the human blood, what they found was, whoa, this protein exists that we had discovered with rhesus monkeys. And if you look at the way rhesus is spelled, you've got this RH here. That is going to be what we refer to as the RH factor. And this is basically just an additional protein that we'll take into account. Now, if this protein is present, we say that your blood type is positive. And if this protein is not present, we say that your blood type is negative. So a common misconception here is, oh, okay, well, if your blood's positive, you got the positive protein, and if it's negative, you've got the negative protein. No, this is just one additional protein. And if it's there, if the RH factor is present, you're positive. If it is not, it's negative. Just like there's not an O protein, it just means there's an absence of the A and B. If there's an absence of this RH protein or this RH factor, we say that your blood type is negative. So there's, again, a lot of other proteins and enzymes that work out great in forensics and are of some importance, but not necessarily of the main ABO naming system that we think of with transfusions. So how common is it? Pretty common. I would say that 85% of the population having it is very common. Mathematically, then only 15% are negative. So does that mean that 15% have a negative protein? No. That means that 15% of the population lack this RH protein, while 85% have this RH protein. So really now we're dealing with 3 proteins, right? We've got the A, we've got the B, and now we've got this RH. So sorry for the cloudiness of this picture. When I blew it up, I got this from your book. It seems like it got a little cloudy. But this is getting a bit more in detail of like the pictures that I showed you before. So check out this guy on the left. If I were to ask you what blood type is this, remember the blood typing name comes from what proteins are on the surface. So I see this erythrocyte, this red blood cell. Looks like they've got the A protein on it. Looks like they've got the RH factor, a protein on it. So this would be type A positive. Now jump over here to the picture on the right. If I were to ask you what blood type is this, before we would have said, well, that's type A blood. And I'd say, boom, You got it. It's got the A protein. Now we're a bit further along. You should know that this is A negative. Cash, why is it negative? There's no negative protein. That's true. There is no negative protein. But the fact that we don't see or it lacks the RH factor makes it negative. It's got the A protein and the A protein only on its surface, no RH. So this guy on the right, that would be A negative. Hopefully that makes a little bit more sense kind of looking at the picture here. Oh my goodness gracious. This little flow chart helps and hurts some kids. I'll go through it in more detail on its own separate activity, but I want to intro it to you first. I'm looking at this top, and this shows donor, who you could give to. This shows recipient, who you could receive from. So give, take. I've got my x-axis, and it's got donors. I've got my y-axis. It's got recipients. So looking at this, this is something that I often have you refer back to kind of check to see if you're right, rather than have you just fill it out, although I think you should get to a point where you could do that. If for some reason this becomes more confusing than helpful, there's other ways to think it through that, like I said, I'll show you in its own activity. But let's take a peek at this. What the heck is this telling me? I'm going to start right here. O negative. All right, who could O negative donate to? I follow this down. Boom, 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 boom. Man, it looks like O negative could donate to everybody. Why? Well, whoever O negative gives blood to, it's not going to be offensive. There is no A protein, there is no B protein, making it type O. It does not have that RH factor, making it negative. Cash, but these guys, they're not getting the proteins that their body naturally needs. Well, no, that's fine. You just can't get proteins that your body's not used to. So it's going to treat it as a foreign invader and come in and clump it up, and it could actually be fatal. So like, look at this, donor. I'll jump from the extreme rather than the universal donor. Remember AB, it's referred to as the universal recipient. And if I were to ask sometimes, hey, who could AB positive donate to or give to? A lot of kids will be like, Cash, AB positive can't donate to anybody because it's got all those proteins and somehow or another it's going to muck it up for someone else. And I'd say, hold on. Remember, you can always donate to yourself. So look at this. AB positive could donate to just this one spot, AB positive. That's it. Jump way down here. Recipient. Who could O negative receive from? Sometimes kids are like, oh, O negative, it can't receive any blood type. It's got no proteins. Any other blood type that it gets, it's going to have some sort of a protein that's going to, be treated as a foreign invader, and it'll be bad news. Well, O negative can receive O negative, but that's it. So if you're O negative blood, man, you're the ultimate giver, and you're kind of out of luck when other people are, the only blood sources that would be available too. And then you can basically kind of walk your way through, which we'll do later with these other ones. But this might be a decent time to just kind of pause, take a peek at this, see if it makes sense, ask yourself some little quiz questions, double check, and see if you're on the right track. Video we'll refer to back later. And here is crunching it all together. Again, has this fluctuated since I made this lecture? Probably a bit, but it's still fairly accurate. Look at this. What's the most common blood type? O positive. And I wouldn't be able to expect or let me rephrase that. I wouldn't expect you to be able to just crunch these numbers in your head, although we will get to where we've got to calculate out these probabilities and explain how they came up with these numbers. Right now is not that time. But if I said, why do you think O positive is the most common? Think about some of the charts we looked at before. O, about 43% of the population had. That was the most common. RH factor, being positive, man, 85% of the population has that. So if you take the most common and the most common, sort of makes sense that it would still be the most common. Whereas if we take a look at the least common and the least common, well, then that kind of makes sense too, right? Look at our AB negative. Remember we said just a small sliver of the population had the AB and 15% don't have the RH. So if you take the least common and the least common, kind of makes sense that you'd get the least common as well. So we will get to where we can calculate these probabilities, but today is not that day. So that wraps up our first section. Hopefully you got something out of it. Got questions? Please let me know. Until we meet again, be safe.